a real-time example, which again I explained in my previous slides, was something about Facebook. Facebook had something called, does anyone remember what the term was? Social inboxing. Okay, just a small recap. What happens is millions and millions of chat histories and various languages and various emojis are flooded in the Facebook database. So there has to be a standalone system which is confident enough to store it and make sure that the right person or the right recipient gets that particular message at the end of the day. Now, an in-memory database, yes, it's fast, but then is it really reliable? So to make it more robust is what our main focus in this project is about. So moving on, this was the architectural design. This is a design which was basically concerned with how exactly the client library has to be shared with the client communication manager, and there's a parsing optimizer and executor, which basically is the SQL querying, basically where the SQL query takes place, and then there's a logger, that's the transaction, and then there's an indexing and the data manager, well, that is basically for the analysis process, and then all the data and everything is stored in a particular collection, that's the database itself. So basically it's a higher level of representation of in-memory database. We'll get into the details and how exactly does this apply in the real time is what we'll be looking at in the further slides. Now, some of the very quick features that we see immediately upon the application of in-memory database would be the real-time data capture and the memory data structure. So how exactly is it comparable to real-time data analysis? Is it quicker? Obviously, because it's easier or it's faster to perform transaction when the data itself is on the primary memory. So by default, it's faster. The performance, there's a huge hike in the performance, faster response time, and increase in the CPU cycle. Now, again, the CPU cycle is a relative term. If you have a high performance CPU, then of course your transaction speed is going to be high. So again, keeping that in mind is something what we again draw upon and improvise in our further slides. So as of now, let's just keep it as increased CPU cycle. Then multi-value concurrency control. Now, when you have a lot of people trying to access the same data at the same time, replications of data gets created, and ultimately there shouldn't be a possibility where the data gets corrupted. So there shouldn't be ambiguity created in any sort of instance. So this makes sure, the real-time analysis makes sure that there is no replication, or it provides a platform where where multiple people can use it. And elimination of network traffic, because of this standalone in-memory database system, even though there are a lot of people using it, the system actually channelizes the traffic efficiently, and there is no heavy traffic monitored anywhere. And coupled tables and indices, again getting back to this in our future slides, there are actually application level diagrams which tells you how exactly the queries gets faster by coupling tables and indices. And the disk space consumption is less than 150 kilobytes of memory. So it's a really low space consuming application. Now, this is the operation task cycle. Well, this can be found anywhere, because this is basically the theoretical part behind the explanation of in-memory database. So here it just tells you how exactly the database works. There's row and column database, massive parallel processing, and a calculating engine. Quickly moving on, these are the commercial databases, that is SAP, HANA, Oracle 10 times, and IMDb Solid DB. So these are the three commercial databases which are slowly drifting towards the in-memory database. So these are the implementational features that they take care. Now, in-memory data grid, this is another type of database design which has a distributed pattern. So here you have individual database servers, there's an application server and the database itself. So this is a distributed pattern, takes care of the social inboxing that I was talking about. So there are various distributed servers around the globe, and they run on in-memory database systems. So there, the concept of having a real-time access and faster queries is actually taken care of. Now this is a transformation. This is where we think that is how the today's system is. Even though there is a traditional database, but then they think by having an ETL, standalone ETL, that the querying are really robust, and they're really robust and they are working, right? But then is it really how the querying must perform? It can be improvised. So we introduced something called as an in-memory system, which actually the ERP, that is the enterprise resource planning, actually loads everything into your particular particular data warehouse which contains all your data, and we have a HANA substructure there. So it takes care of all your data according to your in-memory database schema. And again, now once we have this HANA here, we can totally avoid this. And so that becomes that's the next following transaction where you totally avoid the data warehouse and everything is consoled only with concentrated only with the HANA. And this is the tomorrow system. That is when the entire thing of today's system, we totally avoid the traditional database and it only comprises of your in-memory systems. So conclusion is, yes, we have a space complexity issue. That is, even though you have a standalone system which concentrates on in-memory database, your space complexity, of course, is reduced. Time complexity, as is the real-time analysis and quicker queries, time complexity is taken care of. Migration challenges, yes, in order to do all those changes, every phase requires a lot of research and a lot of research and designing of patterns. So at every stage, they should take care that the previous existing system is always working. So those are the challenges in the prospective studies. The traditional databases are incapable of dealing with dynamic data, whereas nowadays we need a faster processing systems. So now we do have a faster processing system, and this becomes a topic for research and study for the future analysis. Thank you.